Hello, the video today is about molecular geometry and Vsepr theory that stands for valence shell electron pair repulsion. Uh, we are going to talk about the limitation of Lewis theories first and why we need a different theory. Lewis theories that we use for building Lewis structures does not give information on the three-dimensional arrangement of a molecule. That is how the atoms are disposed in the three dimension. And that is called the molecular geometry. For example, the DNA of which you see the picture has atoms that are bonded. We could do a Lewis structure of it, but if we did that, we would have a flat structure. And we do know that in order to be functional, DNA needs to exist in this double helix kind of shape. Now, in order to predict molecular geometry, there are three main theories. And the one we're going to look at today is the first, that is Vsepr. The Vsepr theory is based on the idea that there are so-called electron domains around a central atom in a molecule, and these electron domains are the areas where the electrons kind of live. And these are the ones that will determine and will be responsible for the shape of the molecule. Now, if we look at molecules that we have seen already, say, for example, CH4. So we know that the Lewis structure is one central carbon, and then we have four hydrogen atoms bonded to it. We can see that the electrons in these molecules tend to be in these areas, and I'm going to circle these in pink. So these regions where the electrons are electron domains. So we can say that this molecule has four electron domains. If we look at a molecule like ammonia, NH3, then we can see, and we did, again, this Lewis structure, so we know that ammonia has three bonded hydrogens to the nitrogen and then a lone pair. And we can see here that we can identify these regions, same as we did for the CH4, where the electrons are. We can identify a fourth region, which is this, where there is the lone pair. So one lone pair will account for one electron domain. And so this molecule will have a total of four electron domain. What if we have multiple bonds? So say, for example, we have CO2. Now, CO2 has a Lewis structure with a central carbon and then oxygen bonded to it. And do remember that we do have lone pairs on the oxygens there. Now, I am looking specifically at the electron domains surrounding the central atom. So I am just looking what is around the central atom. So I'm not looking at these lone pairs. I'm looking at what is around the carbon. And I can see that there are two areas, 1 and 2. So these will have two electron domains. Why not four? Because even if there were two bonds, these four electrons that are the ones that constitute the two bonds, remember two electrons per one bond, the electrons, these four electrons, are all in the same region. So even if I had a situation with, say, for example, a triple bond, okay, and another atom bonded here, then I would have, say, another carbon, then I would have one electron domain here. So for a molecule like this, it could be ethine, so H and H. This carbon, when I look at it, would have two electron domains around it. Now, why are the electron domains so important? Because the electron domains are what determines the molecular geometry. So that is how in the space the atoms are going to be distributed. Now, if we have, say, for example, a molecule with two atoms bonded to the central atom, then it's easy to see that because these negative areas try to repel each other, it's going to be easy to see that we have simply 180 degrees between the two atoms. Same if there are three domains, then you have 120-degree atoms. What happens if we have four? Now I'm going to move on to the camera, and so I have a geomag model. So we can see, okay, if I have two electron domains, and so this will be my situation. This is the most distance between these two atoms. I'm trying to make this as far away as possible. If I add one, I can still be in the kind of flat shape. I can stay on the page and I can have this situation. What if I have four? Now, the way we drew it here, and you can see, we kind of drew it flat with a 90 degrees angle. So that will correspond to something like this. But if we think this in 3D, we can see that there is a different option for these atoms to be farther apart than 90 degrees, which is if we do this, okay? So I get this shape, and I'm going to turn it around so you can see. Now, these angles are more than 90 degrees. They're actually 109 if they're all equally spaced. So this kind of geometry would be preferred. So you see how when the molecule becomes more complicated, you need to start thinking in the 3D, and the 3D is not the same as the 2D situation. Now, there are some differences sometimes in terms of those angles. So I was talking about 90, 120. Sometimes you have slight variations because, for example, we were talking about the fact that the double bond has 4 electrons. So it's kind of more negative than a single bond with only 2 electrons. So the angles, like you can see there, would be a bit wider where you have the double bond. And the same if you have a lone pair. So in the case of the ammonia, you can see that you have angles that are smaller in this case because the lone pairs tend to take more space than a bond. So the angle should be 109.5, but it's actually 107, so slightly smaller. However, we're not going to focus on these small variations. So if we remember that for 4 electron domains, I'm going to have an angle that is around 109 is sufficient. And if I remember that if I have a lone pair that the angle is going to be smaller, that's more than plenty. We don't need to memorize all the angles. What we need to know instead is concept is rather more important is the definition of electron domain geometry and molecular geometry. So I'm going to pass back to my model, and I'm going to show you what I mean by this. So if I have ammonia, okay, I can see that if I'm just looking at the atoms, I'm going to have that shape that I was talking about. So it's going to be a bit like this, okay, so in the 3D. So you're going to see something like that. And you can see that you're not going to see, when you just look at the molecule, you don't see the lone pair up here, okay, you wouldn't be seeing it. When you're talking about the molecular geometry, you're talking about how just the atoms are around the molecule. If I am looking, however, at the electron geometry, then I'm looking at the geometry for the electron. So in this case, I would have to consider, okay, say for example that I have this that represents my lone pair, then I would have to consider this, and so I have that extra portion that I need to consider. So how is this going to work? Well, let's look at the Vsepr table that will tell us how we determine these geometries. So you see that the first thing to do is count the number of electron domains. So you see the first column is the number of electron domains. So say we're talking about ammonia. So we said it has 4 electron domains, right? Then you have to determine, is there a lone pair, yes or no, on the molecule? If it is yes, then what you have is that you need to go onto the row that says 1 for the lone pairs. And at that point, you can see molecular geometry is called trigonal pyramidal, and then electron domain geometry is tetrahedral. So that is the geometry you can derive. So what could the question on an exam, because I know that's what interests you a lot, will look like? So we'll say, for example, say I give you ozone, and we looked at the molecule like the infamous O3, and we said, what is the electron domain geometry, and was it is the molecular geometry for ozone. And we have seen that the Lewis structure for ozone was having a lone pair on the central oxygen, and then it was having the bonds. If you don't remember how to do this, I invite you to retry this structure, because we looked at it, right? So 2, 4, 6, 8, that's complete. Now, this has 1, 2, 3 electron domains. So that's what I'm looking at. If I see in 3 electron domains, I need to go look at my table in the column, and I'll show you the table in a moment. So 3 electron domains, and I have to look at 1 lone pair, okay? I am looking just what is around the central atom. I'm not considering these guys because they're not influencing my geometry. Okay, so I'm just looking inside this box. So now I go back to my table, 3 electron domains, 1 lone pair, molecular geometry is bent, and the electron domain geometry is trigonal planar. Okay, so you have here the table, you have the steps that you can look at for determining this, similar as we did in the example, and then you have practice questions. So for example, what is the molecular geometry of BF3? So step 1, you need to do the Lewis structure. Step 2, you need to count the number of electron domains. Step 3, you need to go onto your table. So if I want to do that for BF3, I need to follow the steps, and we can see them here. So draw the Lewis structure, count the number of electron domains, determine the electron domain geometry. Now for BF3, the Lewis structure, if you do it, is going to come up to, remember the boron is an exception, so it likes to have an incomplete octet, so you're going to come out with a structure like this. And then you have electron domains are going to be 3, 1, 2, 3. Okay, so your molecular geometry will be trigonal planar. Your electron domain geometry is also trigonal planar in this case. Notice, if you go back to the table, notice one thing, that if you do not have lone pairs onto the central atom, your electron domain geometry and your molecular geometry are the same. Now, having said that, so answer B, yeah, I got it right. And other example, so SF2, okay, what if you want to do SF2? Again, you need to do the Lewis structure first. The Lewis structure has, the reason why you have to do it is mostly to determine, do you have a lone pair on the sulfur, yes or no? Because if you do have one or more lone pairs, then your geometry is not going to be linear, even if there are just 2 atoms attached. The molecular geometry may be bent if you have a lone pair in there. Now, in this case, you see bent and tetrahedral. Now, if you know the answer to this, you can also work it backwards. If it's tetrahedral, it means you have 4 electron domains, which means that the sulfur must have 2 lone pairs. Why does it come out bent? This is similar to water, okay? So if you have water, you know that the Lewis structure is going to be with 2 lone pairs and then the 2 hydrogens. Now, the 2 lone pairs tend to be on the same side in most cases. So you need to keep that in mind. So with these two lone pairs, 4 electron domains, and 2 bonded atoms, okay, you're going to have a bent shape for the molecular geometry, and the electron domain geometry is going to be tetrahedral. Couple of things. So we were talking about those angles. So how will those angles look like, for example, for water? Well, you see that you have a tetrahedral shape, so it will be ideally 109.5. As a matter of fact, because there are lone pairs, you're going to have some variation. So that angle is going to be smaller than 109.5, and that's all you need to know. So look at this example. We have chlorine trifluoride and chlorine pentafluoride. You see that the presence of the lone pairs restricts that those angles. Notice that here we have 5 electron domains. Okay, so if you look at the table before, you should be able to determine what your ideal angle should be with 5 electron domains, and you can see that this is actually smaller, and it gets different if you have 1 or 2, okay, lone pairs there. This is an example of Vsepr chart, so I do not expect you to memorize all of these things. There is a formula chart that contains some of this information. Please look at the Vsepr chart, and I expect you to be able to use that during any exam. So I don't require you to memorize all the information. But it's very important that you understand how to determine the number of electron domains, because otherwise you're not going to be able to identify where you should go on the table. And also you need to know how to do the Lewis structure, because otherwise you're not going to know how many electron domains there are. So you see how Lewis structures are important. Now, if you have a molecule that has more than one central atom, and we looked before that molecule with carbon-carbon and 2 hydrogen attached, then you cannot determine a molecular geometry for the entire molecule. In that case, what you need to do is determine the molecular geometry around each central atom. So consider as if you had the 2 central atoms. So see the carbon there, it's got 4 electron domains, so the molecular geometry is tetrahedral there. The oxygen, similar to the one of the water, right, that we just did, it has 4 electron domains, but 2 bonded atoms. So the electron domain geometry is tetrahedral, but the molecular geometry is bent. So you will say that you have for this molecule tetrahedral geometry around the carbon and bent geometry around the oxygen. You cannot say this molecule has a whatever molecular geometry overall. There's no such thing. Now, limitation of Vsepr. Vsepr works fantastically well, so we're going to use it a lot, but it doesn't tell you why and how bonds are different. And what do we mean by that? So say, for example, you have the methane CH4 we were looking at. Well, the carbon forms those bonds with different type of electrons, which are in different orbitals, but the 4 bonds are actually identical, and that's an experimental data. And the Vsepr doesn't have an explanation as to why or how that can happen. And another case, which is even easier to understand, if you have molecules that are diatomic, are going to be linear, according to Vsepr, you just have a single bond in there. However, when you look at the bonds between 2 hydrogen, 2 fluorine, or hydrogen and fluorine, then you're going to discover that you have different bond lengths, you have different bond enthalpy, means how much energy will be required to break that bond. It's different. And so they have different strength. And so the Vsepr cannot explain that. It still remains a very powerful, very useful theory.